Everybody, this is AP Physics C, Electricity and Magnetism, and we are coming live to you. Tonight we are going to be studying section 4.4, which is Amperes Law and the law of Biot-Savart. So we are going to go over the lesson with my partner, Roger. My name is Kristen Gonzalez-Vega, and I am coming to you from Frisco, Texas, where I teach at Reedy High School. And my friend here.
Hi, everybody. My name is Roger Siegel, and I'm coming to you live from Sarasota, Florida.
Okay, so I do have a quick announcement. If you've been tuning in all week, then it's the same thing, or last week, it's the same announcement, but we're going to say it at least probably tonight. We are going to be doing some review lessons later on, starting next week, the 6th. This week, we are going to wrap up the magnetism and induction material to finish the content for AP Physics CE&M. The reason we're doing this is that even though magnetism is not going to be tested on the exam, is that colleges have been flexible and working with College Board to give credit to students with the understanding that you guys are going to be learning the material and prepared to move on to the next level if you do receive credit in your course. So we're going to be releasing what those topics are going to be on a weekly basis so that you can tune in and kind of plan what you want to watch and what you want to go over once that review is starting. So today, I want to review with you what we've been talking about last week. So last week, we went over some different units. The first thing we talked about was what happens when you have a charged particle that is moving in a magnetic field. And that charged particle is going to experience a force. And that force is equal to the charge times the velocity times the cross product of the magnetic field.
Can you advance your slides, Kristen?
It is, but it's stuck. So I'm going to have to probably exit out my document camera here so that it is not stuck anymore. So if you guys will just hold on to with me just a second, I'm going to stop this share and I'm going to exit out of something and then we'll go right back at it. So the second thing that we talked about while we're waiting for that is that we looked at what happens if you have a current carrying wire. And if you have a current carrying wire, that wire is going to experience a force, and that force is proportional to the current times the length of wire that's in that field times the magnetic field. So if we go back in here, now we should be unfrozen. There we go. So that force, that magnetic force on that current carrying wire is equal to I times L times B. Truly, it's the integral, but when we looked at that and we integrate across the whole length of the wire, normally it simplifies down to just that ILB. And then the last thing we talked about on Friday was how we found the magnetic field at a point some distance away from a long current carrying wire. So we're going to extend on that today, and we're going to see how we got that equation that B is equal to mu naught I over 2 pi r. Okay, so what we're going to look at today is we're going to look at Ampere's law, and we're going to justify what we call an Amperian loop and how that applies to some different shapes of wires and different currents going through those. We're going to look at how we get that magnetic field using Ampere's law and symmetry arguments. We're going to give an expression for it using a solenoid, and then we're going to do some different conductors, some concentric conductors. And then we're going to look at what happens if we can't use Ampere's law, and we're going to look at the law of Biot-Savart. So we're going to start out, and I just want to, again, kind of look at some magnetic field lines. So if we look at a magnet here, that has that north and south pole. Remember, all magnets have a north and south pole. No matter how many times I cut this up, I'm always going to have a north and a south pole. And if we draw the magnetic field lines, if I sketch some of them here, those magnetic field lines are going to go out that north pole back into that south pole. And the further we get out, the more big those, or the bigger those are going away from the north into the south pole. And we're going to compare that just a second. If I look at a loop of wire, we're going to look at our right-hand rule again. And that right-hand rule says that if we have a current that's going through our wire, then it is going to have, hold on with me just a second, guys. I can see it's lagging again. I'm gonna do is I'm just gonna switch over. We're just gonna go right from the PowerPoint so that it doesn't do that again. So we're gonna go in right into my PowerPoint. Again, I apologize about this. The thing about everybody being home is everybody's online, and sometimes that makes it hard for us to use the internet. So if we look at our segment of wire here, and we've got that current traveling to the right. If we use that group rule, remember you put your thumb in the direction of the current, your finger's going to curl around in the direction of that magnetic field. So in this one, that would be coming out of the page on top of that, and it would be going into the page on the bottom. But the thing that we want to look at is, even though it's going out and up, I'm going to draw it just a little bit different. So we use the annotation, that vector notation, where if we are saying that it's coming out of the page on the top, then we're drawing circles or dots. And if it's going into the page, then we can draw our X's. But I can also represent this by kind of looking, what would that look like? Well, it makes those concentric circles. So if I drew it coming out of the page and going back into the page, and my mouse is gone. Let's see. Roger, can you try to take control? Because for a second, my mouse, it's not letting me.
Yeah, let me go ahead and take it from here, and then we'll get you right back to Dallas I'm sorry, to Frisco in a minute. Okay, so let's go ahead and pick up where Kristen is here. And so Kristen is showing us the field lines. And so as we can see, I'm not showing you anything because I have to go ahead and share my screen. Sorry about that. Kristen, you're going to have to stop sharing your screen for me to do that.
But I can't. My computer is not letting me do that.
Okay. If you want, you could, I believe, leave the meeting and restart and then rejoin the meeting. That might give it up. You could try that.
Yep, I'm just going to have to restart. So I'll join you guys in just a second.
Okay, we'll see you in a minute. Thanks for being so patient with us out there in YouTube land as we work with the technology. In just a second, we're going to get to you. In a minute, I'm going to be showing you a problem with a coaxial cable. And so while we're waiting for that to happen, okay, I'm going to try now. Okay, let's try that. Looks like I'm sharing the screen. All right, and that's my screen. Okay, great. So make sure that that's happening. Okay, good. So as Kristen was saying, we have the magnetic field lines. Remember, they come. Oh, let's try that again. All right, and they come out from the north side and into the south pole of the magnet, and their direction is from north to south. Remember, also inside of the magnet, those field lines keep going. Those field lines are always closed loops, okay? Now, a current carrying wire, if you remember last week, we said that if you have a current carrying wire, you're going to use the grip right-hand rule. That is, with your hand, you grip the wire, and you put your thumb, again, of your right hand in the direction of the current. So I'm looking at this current in front of me, and it's pointing to my right. And so I'm going to go ahead and point my thumb to my right, and I'm going to let my fingers curl. And when I do that, if you're like me, you're going to see that out at the top here, your fingers are curling. And what we're getting is we're getting a magnetic field that's coming out of the paper here. And down here, that magnetic field is going into the paper. All right. And those are our field lines. Great. All right. Now, Ampere's law. Ampere's law is a very, very useful law. And we're going to take a look at it. Now, you might look at it and notice, gosh, it looks a little bit like a law I've seen before, okay? And that law that you're recognizing is Gauss's law. And we're going to talk about, we'll see in a minute how Gauss's law works, but this is how Ampere's law works, okay? We've got a current, okay? We know that magnetic fields come from currents. And so we've got this current, and the current is moving, in this case, straight up. And so by using Ampere's law, we can figure out the magnetic field strength at a point here, or 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 at a point here, okay? And the way we do that is we're going to first, let's talk about what this means. This circle here around the integral sign, that means we're doing a closed integral. Now, when we did Gauss's law, that was a surface integral. In this case, it's a loop. So what we're going to do is we're going to draw a loop around this wire, all right? And we're going to walk around that loop, okay? As a matter of fact, I think I'll switch over to the doc cam, and let's take a look at how that would be, okay? So I've got a wire that's, okay, popping, here we go, in this direction. And there's my wire, current is in there. And I know that using the right-hand rule that my wire has a magnetic field coming out of the board here and going into the board there. Now, if I want to find out the magnetic field at any point through this wire, I can use Ampere's law. And I'm going to write it out here, and it's the closed loop integral of B dot dl is equal to mu naught I, and this is I enclosed, all right? Now we're gonna get into this and kind of see what's going on, see if we can figure it out. In order to do this, I'm going to imagine that we're looking from right here, all right? So we're going to be looking from right here at this wire, and so here's a wire coming out at us, and you can see that there's the current coming out of the page, all right? And so if I'm going to use Ampere's law to find the magnetic field at that point, the strength of the magnetic field, I'm going to at least first get a general sense of what the direction is. So again, the right-hand rule, I put my thumb pointing out of the page and my fingers are curling in the counterclockwise direction. So that means I know that the B field, the magnetic field due to this current I, is going to be about that much. Is going to be in that direction, I'm sorry. Now the question that we're going to get to next is, what is that value? All right, and so how are you doing, Krista?
I'm back.
Okay, great. All right, so I'll finish this up and then we'll throw it back to you, and then we'll get back on track where we were before, okay?
Sounds great.
Okay, good. So, so this is now we're going to draw around this current what's called an Ampere, around this wire, what's called an Amperian loop. And it's the cousin of the Gaussian surface. And so if so what am I going to do? What I'm going to do is I'm going to go all around this loop, and at every point, I'm going to have a tiny little dl. That's a vector. It's very short, and it points in the direction that I'm going around my loop. Okay? By the way, any direction you go is fine. So every one of these is a little dl. All right? It's a vector. And at every point, I'm going to take the dot product of the magnetic field, which is in that direction, and we have B dot dl. Now, there's a reason that I picked a circle and not a square, is because just like with Gauss's law, I'm going to use symmetry so that I never have to integrate this. And so what I do is I'm going to go ahead and say that this is, again, the closed surface integral of B dot dl is equal to mu naught I. And if you remember from last week, if you saw the videos, we said mu naught is the permeability, vacuum permeability, which means that is how easily a magnetic field can move through a vacuum. Okay? And so since we've picked one distance that's the same all the way around, if I drew this right, this radius is always the same, r. And so that means that the B field is the same everywhere. We established that last week. And so I can pull that out of the integral. And then I'm going to integrate all these little dLs. This is a little length. And imagine if you added up the length all the way around this circle, well, what you get is you get the circumference of the circle. And so this is B times 2 pi r is equal to mu naught I. And remember, this is I enclosed, the I enclosed by the Amperian loop, or B is equal to mu naught I over 2 pi r. And so that is one example of Ampere's law. Okay, so I'm going to throw it back to Kristen in Frisco, Texas. And Kristen, what you got for us?
Okay, well, let's go ahead and compare. Now that you just told us about Ampere's law, let's look back at, and you said it's the cousin of the Gaussian surface. So let's look at the two compared side by side, because I think there are really good parallels, and it's something that is something you should remember, right? If we look on the left here at Gauss's law was equal to that surface integral of E dot dA, and that equaled Q enclosed over epsilon naught. So if we look at that left side, and that we had a closed integral, and we look at Ampere's law, and what Roger just said is now we have that Amperian loop, or that Amperian path that we are integrating across, that's also closed. It's a closed loop. And that's all that's dependent on the magnetic field. And the symmetry is what's really important, because you don't pick a Gaussian surface where your electric field isn't the same everywhere, because then you got to do some ugly calculus. And that's not something we want to do, right? So we pick a Gaussian surface where it is the same everywhere. So then that's a constant, and we can pull it out of the integral. Well, we want to do the same thing when we're picking our Amperian path around our wire or in our slab, whatever it is that has that current going through it. We want to draw our Amperian loop or our Amperian path so that the magnetic field is the same everywhere around there. That way, again, it's going to be constant, and it can be pulled out of that integral. So the only thing that we're going to be integrating, while in Gauss, the only thing we actually had to integrate was across our whole surface area. And if you integrate across the whole surface area, what do you get? The surface area of your Gaussian surface. Same thing's going to apply when we go to Ampere's law. When we're looking at Ampere's law, when we take our loop around our wire, right? If we have our wire and we have our Amperian path, well, if we integrate all those dLs up, we're just getting the circumference of that circle. Or if we're doing a slab and we're looking at our rectangle, that's all you're going to get. So you're not actually going to do any calculus with this if you're doing it right, if you pick that right symmetry. Same thing with Gauss's law. That flux with Gauss's law depended on how much charge was enclosed in your Gaussian surface. And with Ampere's law, what our product of our B dot dl is going to depend on is that current that's passing through that surface of that Amperian path. Okay, so there's a lot of parallels there, but then also some differences, right? So let's look at a solenoid. If we take a solenoid and we have the current going through here, so this is kind of a side view of the solenoid, and we can pull up my drawing tool here and just hope my mouse doesn't get lost again. So if we look at this, this is kind of that side view showing the current is coming out of the page on the bottom and going back into the page on the top, right? So I could kind of draw this whole thing. And what a solenoid is I have a big, large slinky here that can be a solenoid. A solenoid is just a coil of wire that's bent into a lot of turns. It could be a few turns, or like my slinky here, could have a ton of turns to it. But we can pass a current through it. I can connect a battery to either end of the slinky and turn my slinky into a solenoid. So a solenoid is just that coil of wire that is has a current passing through it. And if there's a current passing through it, then what do we know is going to be surrounding that current carrying wire? There's going to be a magnetic field. And if we look at kind of one isolated part of that solenoid, I got to see if there's something wrong going on here today. If I look at that one part, and the current is going into the page on the top and out of the page on the bottom, then we can use our right-hand rule and we can determine which way that magnetic field would be going around that. Well, the same thing is going to happen for our whole entire solenoid, is they're going to have that magnetic field that's going around back in those loops. But really, if we compare the magnetic field on the outside of that solenoid to the magnetic field on the inside, it's such a difference. The magnetic field is so small on the outside that we can essentially say there is no magnetic field on the outside of the solenoid. The only thing that we're with is the inside. And so we can use our Ampere law. And again, I'm going to draw on the screen. I apologize till I can find where it is. And we want to know what is the magnetic field that's passing at that point P right there. So if I kind of look at that, I want to make sure that I'm going to first always draw, well, what would be a good Amperian path that would pass through that point P and where there would be symmetry everywhere. And so I'm going to draw my Amperian path, a nice rectangle that's going through point P and is also making that wherever I go along here, anywhere along this path, that magnetic field would be fairly constant. Now, the thing is, if we actually look at the solenoid, it isn't exactly constant everywhere, because as we get to the edge, what do you notice about that magnetic field? It's curving to go out and around. And so we always are going to ignore in physics those edge effects, and we're only going to look at in the center where it's fairly uniform. And so if we go to Amperes Law, and we can say then that Amperes Law is that closed integral of B dot dl, which equals mu naught I through. So what current would be going through that? And if we plug that in, this is really bad, Roger. I think I'm going to have to switch it back to you, because you guys aren't going to be able to see this. So we want this to be good for you. So I need to figure out what's going on with my computer.
Okay. All right. So go ahead, and if you'll unshare your screen, Kristen.
Yep.
I'll pick back up. Okay, great. So let's go ahead and take a look at where we are next. First, let me bring up the PowerPoint. All right, there we go. All right, so a solenoid. Now, what we have with a solenoid, as Kristen was saying, is at least in the inside of the in the part of the solenoid, not over here and not over here, but in the long part of the solenoid, just like whenever we're doing a problem, sometimes we say a very long wire, the magnetic field is constant in here. It is constant, all right? And so we want to use Ampere's law to try and figure out what is the magnetic field in a solenoid, and we're going to derive that. So I'm going to reach across here. I'm going to get some of my notes out here, and let's go ahead and throw up the doc cam so we can see that. Okay. And so let's start with our solenoid, and our solenoid we're going to think is we've got these dots here, dot, 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 and here we've got these X's. And so we're looking at a side view, like if I took a hacksaw and I cut my solenoid in half so that I would be able to see where the current is flowing. And so here current is flowing out of the page up here, and it's flowing into the page here. I'm going to turn mine upside down to be consistent with the PowerPoint. There it is. All right. So there we are. And so we've got this, this B field flowing in this direction. All right, now we're going to use Ampere's law to figure out what is the B field inside this solenoid. And so we're going to start with the fact that the current here is I in this. Okay, so let's say that we have, we're going to draw an Amperian path. And this is not really a loop. This is an Amperian path through this. And we're going to use Ampere's law to find the strength of the B field inside this solenoid. All right, so let's see if we can do that. So remember that Ampere's law, it's the closed loop integral of B dot dl is equal to mu naught times the enclosed current. Okay. All right. And we're going to use this to find B. Now, I'm going to go around this loop in a clockwise direction. And I'm going to start here. Now, as I go from here to here, what we said a minute ago is out here, B is equal to 0. So there is no field here, B, going in that direction. There is no field here, B, going in this direction. And there is no field, oops, from here to here, B, going in that direction. Okay, so my B is 0 here, here, and here. Now let's look at these next three parts. Okay, this line, and this line. Okay, now I'm going to call this, okay, well, let's call this length L from here to here. All right, now, how many, so let's go ahead and see what B dot dl is here, here, and here. I'll call this little point A, B, and C. So let's go ahead and see A right here. What is the, using Ampere's law, what is B dot dl? Well, if you look at this, look at my B field. My B field is pointing to the left. This is my B field. I drew it over here before. I'll draw it here. I'll draw it here. There's my B field. And my B field is parallel to, perpendicular to my DL. So that means that as I go along this part of my Amperian path, here, I'm going to have 0. There is no B dot dl there, 0. And the same thing here, B dot dl is equal to 0. So the only place where I have a B dot dl is along this line. Okay. And so what I'm going to say is that B, which is what we're actually looking for, times the dl. Well, when I add that up, that's the length L, is equal to mu naught times I enclosed. Now, what is I enclosed? I enclosed is going to be the number of wires that I've enclosed. In this case, this is 3. And Kristen, do I use a small n or a capital N for that one? I want to be consistent. Do you remember?
The small n is the number of turns
Yes.
per length. Big N would be the total number of turns.
Yes. Okay, so this is big N. Thank you so much. Okay. And so to be consistent, so that is N. So I've got 3 of those. And times I. So let me write that again. Sorry, that didn't come out right. B dot L is equal to mu naught N times I, or B is equal to, zoom out a little bit here. B is equal to mu naught I N over L. Now, this N over L, that is the number of turns per unit length. And so B of a solenoid is equal to mu naught I little n, which is the number of turns per unit length. Wow, and that's how we find the B field inside a solenoid. So you'll find that in every physics book that you look into. It's one of the classic derivations of what we're working on. Okay. Now, Kristen, how you doing over there? How's the technical situation?
Well, I switched over my wireless, so I think that it is okay.
Okay, good. So I'm going to throw it back to you. And so let's get back to Frisco, Texas.
Okay, so I'm gonna have to have you stop sharing for me, Roger. So there we go. So let's look at another application of this. So let's look at a conductor, a wire. If I have a wire that has a current that is traveling kind of out at us like this, and we have a radius of r for the whole wire, and we want to know what would be the magnitude of the magnetic field at a couple different places. So this should kind of also bring you back to fun, wonderful memories of Gauss's law, except we were finding the electric field inside of conductors and inside of insulators. So we want to find first, let's do if it is bigger than r, right? So if we have a distance away that is bigger than the radius, let's do that one first. So if we pick a point here, and let's say I want to know at this point P, what is that magnetic field? So the first thing I need to do is identify my Amperian path that would give me symmetry. So how could I draw an Amperian path that would give us the same magnetic field? And that would be if I draw my Amperian path, that's that nice closed loop around my wire. And so if we say then that the integral of B dot dl equals mu naught times I through, then if we look at that, we can say, well, if I go all the way around, my B field is the same, so B comes out. If I integrate my dl all the way around, what do I get? Well, I get a circle. And so then this is going to be equal to 2 pi times r. And what you're going to notice is I'm not going to use big R, because remember, big R is a very specific value. Big R is the actual radius of the wire. I want it as a function of R any distance away from that. So this would, R could be just outside here. It could be 20 kilometers away, right? It is for any R around that. And so that equals mu naught times, well, if we look at that Amperian path, what current is going through the face of that Amperian path? All of the current is being enclosed in that loop, so that would just be the current in the wire I. And so if we want to just solve for B then B would equal mu naught I over 2 pi r. Ah, that looks familiar, doesn't it? That's what we looked at the other day. And we didn't derive it, we just gave it to you that outside a long current carrying wire, the magnetic field is mu naught I over 2 pi r. And now you can see why. We can use Ampere's law to prove that. But what if instead, and I'm going to erase this original one, I want to know what the instead magnetic field is if I have a radius smaller than r. So if we are anywhere inside of that, then what would be the magnetic field at some point in there? So again, we're still looking at what that Amperian loop is. It's still a circle. I'm still going to start integral of B dot dl equals mu naught times I through. So you're always starting there, and then you're looking at two different things. What is my Amperian loop, and what would that dl be, or what would that total length of that loop be? And then what also is the current that is going through your Amperian loop? So that's where we have to get a little bit tricky here, right? It's still a circle. We're still using 2 pi r. It's still little r, because I want to know for any r from 0 up into r. So on that left side of Ampere's law, we are always using little r because it's for a function of any radius away. that equals mu naught, we have to look at how we're going to get the I through there. And so if we say that the current density through here is uniform, if it's the same current at every point in that wire, it's kind of like when we looked at charge density. We have what we call current density. Current density is J, and current density is equal to, excuse me, that current that's going through per area, just like we had our charge density, which was the charge per area. So if we look at here, if the whole thing has the same density as the part, then we can set up what we call a ratio of those. So I could say that the J of the whole thing, the whole wire, is equal to the current density of just my Amperian loop. And so then I could say, well, the area of this whole thing is equal to pi big R squared, and the whole current is I. Let me make that a little bit better to see. So we can say that the total current, which is I, over that pi big R squared, is equal to my current that's just going through my Amperian path, just that part that I want, over the area of just that, which would be pi little r squared. And so then it's rearranging and solving for what that I through is in terms of the total I. So through is going to be equal to, well, if I look at my equation, my pi's are going to cancel out. If I bring my cross multiply, then my I through is going to be equal to I times r squared over big R squared. And that's what I can plug in for the I in the equation. And so when I plug that in, then I get, this is I times little r squared over big R squared. And then if we solve for B will equal mu naught times I. Well, I can look and cancel out this r with this squared, and then I have divided by 2 pi times big R squared. And one of those little r's still. So that would be what it would be for anything inside here. I could plug in any r from 0 to big R. And then the next thing we need to be able to look at is, well, can we graph that relationship? And so if I graph that relationship, and it's similar to when you were graphing the relationship of the electric field as a function of the radius. So it's not like you have to memorize what these graphs look like. We literally just derived what the relationship is. So we're just looking at what that relationship would be. So if we look at from anything between 0 and big R, what kind of relationship is there between the magnetic field, B, and my radius r? Well, where is r in the equation? Is the r on the top, on the bottom? Is it squared, square root? Well, r is on the top, and not only is r on the top, it's just r. So the relationship between B and r would be a direct relationship. So as that radius increases, my magnetic field is increasing proportionally. It's a linear relationship. And then anytime we get outside of r, well, now I'm looking at my bottom relationship. And now the relationship between the magnetic field and the radius is an inverse one because r is now on the bottom. So then it's going to have that inverse relationship decreasing. Okay, and as we went further and further out, it'll asymptotically reach infinity, and that would be the graph. All right, Roger, do you want to do the concentric one?
Well, yeah, let's see what we can do. I'm gonna take you through this. I'll tell you my what I love most about getting to teach this class is that everything that you learn pretty much in kindergarten through 11th grade in math, we're going to use. So, and there's a lot of geometry here that we're going to get into, but that's why it's so fun. Okay, so there is, let me see if I can do this in 5 minutes. I'm going to go kind of fast, but I think you'll be able to follow. Okay, so there is a kind of a cable called a coaxial cable that you, I'm sure, have seen before. And the reason I know you've seen it before is because you live in the modern world. Where'd my coaxial cable go? Okay. Okay. Now, all right. Can we see my stuff? All right, here. Now, this is a coaxial cable. You've probably seen it as it brings cable TV into your house. It's got threaded on one end, and on the other end, I want to show you I've
And you got to share with us, Roger.
I'm not sharing. Oh my goodness. Thank you so much for telling me. Let me try that again. Okay. There we are. Okay. Thank you, Kristen. Okay, so you can see that this is a coaxial cable, and coaxial means they have the same, and they have the same axis. And there are actually two different conductors in this cable. There's a little one in the middle, which you probably can't see as clearly as I wish, but it is copper. And then on the outside, we have these aluminum wires, and they're separated by a little bit of plastic insulator. Right? And this brings the internet into your house, and it brings the cable TV into your house, and lots of things like that. Now, as far as finding the the magnetic field at different points in this coaxial cable, well, when we apply Ampere's law, like Kristen just did, and we come out here and we measure to the outside, well, guess what? We're going to find that we are enclosing the same values that in this problem that we did in the last problem. In other words, the first two answers here are exactly the same as what Kristen just showed us. And so that is when R is less than A, and I'll put this over here, and you can rewind the video to see it if you want to. We have that B is equal to mu naught I over 2 pi R squared times little r. Okay. And similarly, when R is between the inside conductor and the outside conductor, this insulator in here, we're going to have the same answer that Kristen had on the second part. And that's going to be that B is equal to mu naught I over 2 pi R. And that's because when we draw an Amperian circle or loop around here, we enclose, we only worry about what's inside the loop. And that's why we have current enclosed. Just like when we did Gauss's law, we were only concerned with the charge that was enclosed in our Gaussian surface. Now in Ampere's law, we're only really interested in the current enclosed in our Amperian loop. Now, it does get a little tougher when we go between here and here. So this is where the fun happens. So let's go ahead and imagine that we have a circle that is here, and its radius is little r from there to there. Okay, now in a coaxial cable, the current goes in opposite directions on the inside and the outside, and there's a reason for that. And the reason is what it does is, since you have opposite magnetic fields forming, any fields, magnetic and electric, that tend to form inside the insulator between the two conductors and not outside the coaxial cable. And so it becomes like a shielded cable that is very resistant to electromagnetic forces from the outside. Okay, now, so let's see if we can do this. What we've got to do is we're going to apply Ampere's law to this. And so what we're going to say here, let's see my notes here, is we have B dot, the closed surface integral, let me come over here, of B dot dl is equal to mu naught times I enclosed. Now, here's the hard part and the fun part, is finding the I enclosed here. All right, so that's what we're going to do. We're going to take a second on that. So I enclosed is equal to, well, first we have this current in here in the middle. So that is I, and that's going to be positive. minus the current from the outside. Well, how much do we have? Well, we have the total current on the outside times whatever fraction of the whole is enclosed, whatever fraction of the whole is enclosed in this washer. In other words, we're going to put the area of this washer divided by the area of the big whole washer conductor. And so that is pi r squared minus pi b squared over pi c squared minus pi b squared. And that is our enclosed current. Right? And so now what we're going to do is we're going to use that over here. All right, come back over here, and I'm going to say that B, and now DL is, again, when I integrate DL, I'm going to have a circle. So that's 2 pi r is equal to mu naught. And now we're going to have I enclosed. And we just said that I enclosed was I minus I times, and I'm going to cancel out the pi's, r squared minus b squared over c squared minus b squared. Okay, and so this is going to be b dot 2 pi r is equal to mu naught. And now what I'm going to do, I'm going to bring the I out front here, and I'm going to get a common denominator. And so this is c squared minus b squared over c squared minus b squared minus r squared minus b squared over c squared minus b squared. And so we have b times 2 pi r is equal to mu naught I. And then let's look and see what we have here. C squared minus b squared minus r squared. We're going to distribute this. This is going to be plus the b squared. So we're going to end up with c squared minus r squared over c squared minus b squared. And so b is equal to mu naught I over 2 pi r times c squared minus r squared over c squared minus b squared. All right. Now, so there is that piece. And again, fun with geometry, right? So now the last part is when r is greater than c. Now, if r is greater than c, let's check it out. We've got, here's our current coming out of the page. Here's our current coming in the page. If I go out here, the total current enclosed is 0. And so here we have B is equal to 0. And so the last piece that I'm going to do before we throw it back to Frisco, Texas, is to fill in this guy. And this shows the B versus R for our previous problem. So again, the first two parts are exactly like what Kristen did in her first two. Right here, this value here is, that's capital A, and this is mu naught I over 2 pi A, okay? And then we get to this point and we're decreasing, but then we start adding negative current back in. So we decrease even more and we get here to C at 0. And I want to show you something that AP sometimes does. They want you to draw the 0. So don't forget, we went a little short on this graph, but AP won't. So there's a 0 there. We're going to make sure we draw it, okay? Well, that's a pretty cool problem. All right. I'm going to throw it back to Frisco and we're going to take it on home.
Thanks, Roger. We are going to look at one more thing. I'm kind of sad if any of you are still watching with all this technical stuff going on, but we did not have a chance to do Savart, which I love doing. So we may be able to pick that up again later. It is if you cannot draw an Amperian path, maybe you don't have symmetry everywhere on that Amperian path, or that magnetic field is the same. Like here, if I were to look at this wire, well, if I try to draw some Amperian path here, the magnetic field is not going to be the same everywhere because of all these little elements of the wire that have their own current going through it that are contributing to that field. So we've got to treat it a little bit differently. And it's kind of like when you have an arc of charge or line of charge and you have to to break it up into little parts. And so hopefully we'll have time to come back there. I'm going to set us up because I don't want to take you too long after class, but I want to just set up a really good problem, and it'll kind of be your homework. So I want you to look at this, screenshot it. You can access it. It's from the 2018 E&M exam, and it's question number 3. And I love this problem. It's 2 wires. Those 2 wires are running kind of perpendicular to each other, and one is on top of the other. So you have both a side view and a top view of those 2 wires. And if we look at this side view, you can see that there's current going to the left on the bottom, and then there's current coming out at you on the top, right? So it's kind of like this. And we want to look at this point P, which is a distance D from wire 1, and also vertically a distance D from wire 2, what would be the magnitude of that field? So we're going to kind of just set this up real quick, and then I want you to work it out, and we can, if we look at these, let's take each individual wire on its own. Let's look at due to the magnetic field be at point P. Well, if we use that right-hand rule and we say that we have our current go to the right and we have our grip, then we're going to be into the page, out of the page. So up at the top, we would have a magnetic field going into the page due to that wire. And if we look at the wire on the top, that current is coming out at you. So again, thumb out, grip around, we're going around counterclockwise. So I'm going to draw that counterclockwise around I. That means at point P, that magnetic field is going up. So we have 2 contributions to the magnetic field at point P from those 2 different wires. And if we want to look at how we would use Ampere's law to derive that magnetic field due to just wire 1, let's look at just wire 1. I already really drew my Amperian path there by drawing that magnetic field around. And so we can set that up easy because we know that the integral of B dot dl equals mu naught times I through. We're looking at just wire 1 right now. So if we say, well, due to just wire 1, that would be a magnetic field that would be constant everywhere on that path. So different circle would be pi r, but what the circle? It's D. And that is the I going through. If we look here on the problem, I1 is just I, is 2I. So we're talking about wire 1, that's just I. So then we could say that B is equal to mu naught just that I over 2 pi x time R is D. Hello.
Hello? Okay, now we
It
can hear you.
booted me out. Yeah.
Okay.
I think there's too much Paw Patrol going on upstairs is really what it is. So we'll have to shut that down for tomorrow. So if we look we had that mu naught I over 2 pi D. If we look at what the net field would be there, well, that would be the contribution of both of them. And we've looked at when we have them both going the same direction or opposite directions and subtracting those fields. But here, these are perpendicular to each other, right? One magnetic field is going up, one magnetic field is going into the page. And so we've got that right angle. So what do we do with 2 vectors that are a right angle to each other? We use Pythagorean theorem. So that's kind of how I want you to set you up, but I want you to do the rest of it. We're going to let you get back to your families and dinner, and we will come back tomorrow to do a little bit more of the magnetism with you guys. So from Frisco, Texas, I am Kristen Gonzalez Vega. Thank you so much for being patient tonight. Tomorrow will be better. Roger?
Thanks so much for tuning in, and we hope these are helpful.